As I was saying, the first talk is from Professor Klaus Bogenberger from Technical University of Munich. Klaus leads a big research group there. Something about Klaus, so he studied civil engineering at TU Munich back he finished in '96, so 3 years after I was born. So that's impressive. He then then he got his PhD on adaptive fuzzy systems for coordinating traffic responsive ramp metering. And since then, he worked on various aspects of the problems of future mobility systems, first at BMW, then in another company called Transfer, and finally at TU Munich. His research focuses on theory of traffic flow in urban road networks and motorways, all the way from studying the data sources to traffic simulations and analysis of potential scenarios of the future. Currently is focusing on the development of innovative traffic control methods, which incorporate vehicle data and improve traffic situations for pedestrians and cyclists. Today, in his talk, Future on-Demand Systems, is going to kick off the workshop and also give an overview of the research he's been doing with his team for the past 8 years. I've personally been following his group's work a lot, and I really like it. So I'm personally very excited to hear more about the topic. And that's why I give you the stage, Klaus. Go ahead.
Thanks, Joelle, for this very kind introduction and the great honor to kick this workshop off. I will give my very best, I can promise. And at the beginning, I want to emphasize that the research I'm presenting is the research of a bigger group. It's not just me. There are several PhD students, master students involved in the projects that I'm mentioning. And I will try to give an overview about the results that we obtained in several studies and projects over the past years. The agenda of the talk is divided in 7 parts. I have about 30 minutes, I heard. At the beginning, I will define what we understand under mobility on-demand services and how it is defined in Germany. There might be other definitions around the globe. Then I will focus on simulation of ride-hailing at the beginning before I come to ride-pooling. I will also mention how boarding processes of such mobility on-demand services could look like or how they could be organized, because in the first part, I will mainly focus on the operational aspects. Part 6 are some side aspects or new aspects. And at the end, I will tell you what we think our future research will be. But of course, this can always change. So let me start. Under mobility on-demand services, we understand more or less 3 different subtypes. The first one is on-demand ride-hailing. Then we have on-demand ride-pooling. So hailing is more or less one person, while pooling can be several persons. And we have on-demand car-sharing systems. As you can see, here are the logos of some companies. There was a couple of years ago, there were 2 very famous German companies in the area of car sharing called Car2Go and Drive Now. They merged. They were also sold by Daimler and BMW, and they're now named Share Now, and they still operate an on-demand car sharing service in many cities in Germany and in Europe. This company also offers e-hailing service. You can see the similar logo. This is then now called Free Now and is an on-demand ride-hailing service. You can see that on the left here. Most of you know the very famous brands Uber, Lyft, and Didi, which we consider ride sourcing services. And over the last couple of years, we find more and more ride pooling services here in the middle. So the idea is to combine trips and to use more or less the whole capacity of a vehicle. In Germany, we have a very famous service in Hamburg, launched a couple of years ago, called Moja. Moja is a Volkswagen company, and you will see also results of this service, since we were involved in the scientific evaluation in Hamburg. There are other services available for ride pooling at the moment. All these services have one problem. They need a driver. A driver is expensive and makes such services less profitable. And I think that in the near future, we're also going to see the problem of missing drivers, because we can already see this in public transport. It's really hard to find bus drivers, and it would not be amazing if we also will see missing ride sharing, ride pooling drivers in the near future. So lots of people talk about automation. There are first automated vehicles available and first automated mobility on demand services. A very famous one in Phoenix, Arizona. Here a little video. This is a so-called robo shuttle service, and this is a famous Swiss newspaper, and the journalist made a trip and tested the system. Worked very well. On YouTube, you can find lots of videos with problems as well of such robo shuttles at the moment. But if people tell you when will this start, that vehicles drive automatically, then you can tell them it already started. You can go on YouTube and find the first videos, and you can really see it. Actually, I've never tried it by now. Also in Germany, we're going to see such a service soon. Sixt, a very famous car rental company, together with the company Mobileye from Israel, will launch a service in 2023. Of course, the fleet size will be very small, and we are very interested in seeing how it works and how people accept such a service. I have to say that this will not be fully autonomous at the beginning, but the idea in a later stage of the project is also to be autonomous. Also, Volkswagen and in brackets Moja are testing autonomous driving for their Moja service. I just recently saw a vehicle like this in Munich driving around. So they are already testing on real streets their automated bus. And we also expect in the near future that Moja will test autonomous robo shuttles in their Hamburg service. So now you know what I'm talking about. There are a couple of questions in the chat. Okay, that's not from here. Yeah, about simulating such things and the questions and the research behind it. How does such a service work? Of course, it's a mobile app-based service where you as a customer are located. You can type in your destination, and the service operator sends you a vehicle or makes you an offer first, and if you accept the offer, the operator sends you a vehicle. You get the estimated time of arrival, and of course you get the cost for your trip, and then you can decide to accept this offer or to reject. In ride hailing, it's more or less the following situation. You have red and blue dots here. These are two different customers, and both customers have specific origins, more or less the points where they are currently positioned, and two different destinations. The operator has several vehicles in an operating area, and the operator has to decide which vehicle he sends to the customer. and then the customer is driven to its destination. By now, this is done by a driver. In the near future, this can be done by an automated vehicle. Indifference, ride pooling. So same two customers, same origins, same destinations. In this case, the idea is to combine the two trips. So at first, there would be a vehicle driving to customer 1, then customer 2 is boarding, and then both are driven to their destinations. When you think about simulating such a system, you have to consider several aspects. I mentioned here some of them. The first one is the street network. So what are you thinking about concerning travel times, travel distances? Are you working with the real distances or Euclidean distances when you try to simulate something like this and optimizing a service like this? Are you working with static or dynamic networks, deterministic, whether stochastic traffic simulation? And is your service having the full or limited knowledge, which would be more realistic? On the demand side, of course, there's a certain decision process a customer has to make. He probably does not accept very long waiting times. The question is, are you simulating monomodal or multimodal? Are there intermodal trips allowed? What is the mode choice model you use? Then you have to think about the fleet that you are looking at. What is the fleet size? What is the fleet composition? All electric, mixed engines. How many seats do you have? Different number of seats. And are you having a dynamic or a static fleet? So is the fleet size always the same, or is it changing? And what's the number of active vehicles at the moment? Then your service has a certain infrastructure. Are you having depots, or are you using on-street parking and on-street charging, for example? What is the boarding location you are using? Are you using bus stops, or is it a door-to-door service? And what's the operating area? Then there are several service attributes as well that you have to define. So you need to have a pricing strategy. The pricing strategy affects the mode choice, probably. So if you have a high price, people are not willing to use your mode. What are walking distances and time constraints? For example, detour times. People might only accept certain detour times as well. And then, of course, several fleet control strategies. Routing plays a very, very important role. Charging, rebalancing, and many things like this. We developed an agent-based simulation framework with which we are mainly working. Here a little animation about that, and a short announcement or advertisement. This simulation framework is called FleetPy. It's an open source agent-based in Python written simulation framework available on GitHub. So whoever is interested in agent-based on-demand simulation could have a look into it. It's open, it's free of any cost. And if you want to read about it, there's a preprint available on the archive. Both are mentioned here. So we used this framework at the beginning to optimize hailing services. And the question was, how do you control such a hailing service? So remember, this is the situation where we just pick up one person and drive this person to his or her destination. And the first question is, what customer vehicle assignment strategy are you using? So which vehicle are you really sending to the person? And of course, there are several different options available. We tested several different algorithms. and all the different algorithms are available in the FieldPy environment. The second question we tried to answer was, how dependent is your service on the quality of the demand forecast and the vehicle repositioning strategy? So as you can imagine, it's very important to estimate the correct demand, because the demand more or less also affects the repositioning strategy. Repositioning means that in advance, even without a request, you are already sending vehicles to certain locations in your network because you anticipate more or less a future demand in this area. And the more precise you have this demand, the better you can position the vehicles, the shorter the waiting times are for the customers, and the better the overall service. Therefore, for the repositioning strategy, we developed a specific rebalancing or imbalance density function. So the question is your system imbalanced, which means you do not have enough vehicles in a certain area of the network where you expect a high demand. This was already been used, similar approaches in free-floating car-sharing systems. Here we advanced the method a little bit with a specific density estimation method to estimate the precise future demand and then forecast the imbalance. And if you have an imbalance, then you can proactively send vehicles to the areas with vehicle shortage. Very interesting is a comparison of free-floating car sharing and autonomous hailing. We had a data set of DriveNow for Munich, and DriveNow was operating in Munich with approximately 600 car sharing vehicles. So we had this demand, the number of trips that were operated by this free-floating car sharing service provider. And then we tried to figure out how many vehicles would you need if this demand should be served by an autonomous hailing service. You can see a function here. These are different strategies with different waiting times and detour times and things like this. And the dashed line here at 150 shows more or less the best value of the objective function. So the question, the answer is you roughly need about 150 robo hailing vehicles to serve the demand that is or was served by a free-floating car sharing service. This is 25% of the vehicles. Of course, these vehicles drive much more. They almost do not park. They are almost all the time in operation. And also we checked for prices, and the price could also be decreased from around 31 euro cent to about 20 euro cent. Now to pooling. So this was hailing, now to pooling, and there's a very important factor in pooling called scaling. And at the beginning, we developed an analytical model based on the so-called shareability. And analytical means, in this case, we didn't use at the beginning the simulation framework. We used a more or less geometric model displayed here on the upper right. And based on this shareability, there's a shareability index with several parameters, system or service parameters and city parameters. Therefore, you need the average velocity that can be driven in a city, so a very global value. You need to define the operating area. You need to have an idea about the pooling demand. You can derive that from the individual vehicle trips, for example. You need to think about the detour time, the maximum waiting time, and the boarding time in your service. And these are all parameters you need. So this model is very helpful when you think about implementing a ride pooling service in a city, because you don't need any simulation at first. These are very global parameters, usually very easy to get. And then you can try to figure out how the shareability in this city looks like. And here are some results. For a detour time of 5 minutes, a maximum waiting time of 5 minutes, and an optimal boarding time of 0 seconds. So the passenger jumped more or less instantaneously in the vehicle. And in this case, we compared the analytical model with simulation. And what you could see is this is the following: that with an increase of the request density displayed on the x-axis, the shareability increases. So, and almost with a request density of about 5 requests per square kilometer an hour, so that's the unit for the request density, you are near 90% of shareable rides. So lots of people could share their rides. This is for the case that we are using Euclidean distances. Of course, this is not very realistic in a city, because you're going to have a street network and no Euclidean network. And the whole density range shows a similar behavior in the simulation case and in the analytical model. Of course, not all shareable trips can actually be realized due to assignment constraints. So there are certain objectives that you need to consider. Then it further decreases. You have to be aware of that, yeah, by up to 50% when changing the optimization objective from just putting them all in the vehicle to save distances or minimizing vehicle kilometers traveled. So at the beginning, you just try to get them all into the vehicle. Now you try to minimize the distance of your, the driven distance of your vehicles, or you try to minimize the vehicle kilometers traveled. Then when you change to a real street network, you also need to think about that, that this further decreased the shareability. And now we are in a realistic range, almost realistic, because when you apply temporal and spatial inhomogeneous travel times, which a real network has, then the shareable rides further decrease. So from the optimal, theoretically optimum, at the beginning, you need to be aware that the real shareable rides decrease significantly. We tried to estimate percentages for this degrading. It's possible, but I would say it depends. We didn't really do enough networks to have stable results of these parameters. When you simulate pooling services, so no analytical anymore, then you're gonna see what is really, really important when you implement a ride pooling service. On the x-axis, and this is a study for Munich, Germany, you see the simulated demand. So from 1 to 15% of the individual trips in Munich, we have about 2 million individual trips a day in Munich. Therefore, you need a specific fleet size. So for the 1% demand, you need about 200 vehicles, while for the 15%, you need about 3,000 vehicles. And when you then look at the relative safe distance, you see that up to a degree of 5%, you're gonna have negative relative safe distance, which means by implementing such a service, you induce further vehicle miles or vehicle kilometers. So the vehicles drive more than before because they're empty trips to the customer, pickup trips, and the pooling effect is not that high. But from a demand of 5% on 5% and higher, you're going to save distance up to almost 20% in the case where people accept fairly long detour times of 60%, okay, or detour kilometers. And I mean, that's the case if people are patient and accept detours. And if you have a really high demand, you're going to have lots of shareable trips. And then this system is also very, very beneficial for the city because you're going to save lots of mileage. So the idea or the result, and this is more or less the result of all people that work in this area, think big. When you talk about ride pooling, think big, implement a service with lots of vehicles, and try to get as many people as possible into your service. This can also be illustrated in the 15% scenario, so where you almost save 20% relative distance. You see in green a reduction of flow, more or less, on all major roads in Munich. You still see some red. These are minor roads where people need to be picked up. But compare this to the case of the 1% scenario, where we have induced further vehicle miles. You're going to see red. So lots of roads in Munich would get more traffic, more or less, more vehicles. Then the question is, up to now, we were only looking at services with no reservation and no relocation. So all the simulations I just showed had no reservation and no relocation implemented. And what you could see is that if you implement a reservation-based service or a relocation, you would be able to save more or less to serve all your requests. Yeah, this is on the left part of the figure. So almost all requests that you get can be served in a reservation-based system. This is fairly easy, especially in this case, because this was a scenario with reservation only. But also relocation improves the situation drastically in comparison to the just basic on-demand service that I was talking before about. And another thing is that also in lower demand scenarios, you already get a mileage beneficial. You're already going to save distance. In the case of a reservation system, even with a very low demand with the 1% scenario, you end up at 0, so no more trips. And from this on, you're going to serve lots of distance. If you look at the number of vehicles here and the relative number of vehicles that are occupied, you're going to see that in the case where we have no reservation and no relocation, we have here 2,000 vehicles. This is the time per day. And in most cases, we only have one customer on board. Okay. And this is with 120,000 trips a day. So this is I think the 10% scenario. So it's not the 15% scenario and a 40% detour acceptance. And you see over the whole day, we never utilize the full fleet. and only few vehicles are occupied with 4 or more customers. You don't even see that, more or less. Yeah, you see 3. There might be really a few with 4, but in this case, 4 vehicles was the maximum number of passengers. If you implement relocation, you add empty vehicle trips, because you try to anticipate the demand, and then you send vehicles to the areas of expected higher demand. And in this case, you're gonna see the following. During the peak, the fleet is almost fully utilized. You get much more people in the vehicles, especially the 2 and the 3 a little bit, and drastically improves the situation in the reservation scenario, where you can now also see clearly that there at the morning and in the evening peak, that we can see occupancies of up to 4 passengers. I mentioned before that this was a fully reservation-based simulation scenario. For the upcoming TRB, we have a paper accepted where we did a simulation of a mixed operation. So here, some of the people are allowed or are reserving their trips, while others are fully on demand. The problem in this case is that this is a really large vehicle routing problem that you create. And what we do is more or less that we solve the problem for the pre-booked reserved trips, and we implement that later in the on-demand cases, or in the on-demand time horizons, and we integrate this solution. And yeah, the suggested algorithm that we developed works fairly well, and we got pretty good results, which you can see here. This is more or less an objective function displayed here on the left, different scenarios, but all of the scenarios have pretty much the same, that at an area of about 50% pre-booked trips, you're going to see an optimum. Lower is not good and higher is also not good. About 50% would be perfect if 50% of your trips that you want to serve are pre-booked cases. On the right part of the figure, you're going to see what this means. Look at the 50% bar here. This means that you have booked cases, you serve those customers, but all the booked cases can be served. There are no ones rejected. No one is rejected. There are some on-demand requests. Some of the on-demands have to be rejected. That's always the case. There are always people that you cannot serve, but all the pre-booked can be served. And if the pre-booked gets higher, then you also have to reject pre-booked. And that's not good, of course. If a person is booking a trip, you need to guarantee that in your service. Otherwise, the service quality is really bad. I mean, that a customer is pre-booking because he wants to be sure that he can make his trip. I think I'm jumping a little bit now to one further slide here. We have been calibrating the simulation with real data. As I said before, we were very happy because together with our colleagues from the Karlsruhe Institute of Technology, we were the scientific partners at the beginning of the MOIA service, and we got lots of data from them, from app requests and so on. We did a big survey to estimate the demand, especially the colleagues from the KIT did that. And we could compare more or less our simulation results with the real service. There were about 400 vehicles operated at that time in Hamburg. What was also possible in this project, that we could combine their agent-based travel demand model with our ride-pooling fleets simulation model. And as I said before, mainly for calibration purposes, this was really, really interesting. A very nice visualization also of this Hamburg network. Some key findings of ride-pooling bus service. Ride-pooling plays an only minor part in the overall transportation system in Hamburg at the moment. As you can see, only a very small modal share compared to all the other modes that are implemented there. If we would implement automation, then this would significantly increase, up to 1,200%. So we would end up at a mode share of around 1.3% of overall trips. Mainly, this can be seen here, from vehicle trips, but unfortunately also a little bit from walking. And if we would additionally implement regulatory measures, fees and things like this, the mode share could be further increased in Hamburg, almost up to 3%. One final, and this is more or less the final research part that I want to explain. A question is, now that we know that scaling is more or less very, very important, so big fleet size, lots of customers, everybody would say, okay, this is a monopoly, but the monopoly is not good, because then the price can get really, really difficult, or the pricing strategy, as we see in the energy market at the moment. Same scenario could more or less happen if you only have one ride-pooling operator. So what is if you have two? Are there ideas to combine more or less two operators? We developed the idea of a so-called broker system. This is a central entity, which the city, for example, could play. And this central entity more or less collects the trip requests and then gives the trip requests to the, in this case, two operators. So in this case, we had two operators, and then they can make their offers. So there are different options, and then the user can select if he accepts the offer of the operator. And if you do this in a smart way, then you can, even with two operators, be very, very beneficial, almost as beneficial, displayed here on the right, the two case, instead of if you only have one single operator. So of course, both would not have the same as they would be alone, the same benefit, if it comes to relative safe distance in this case. But you could be still very beneficial. Both would be inducing no further vehicle trips, and this is a good result and a good information for you, because this means we could allow two operators, but the two operators have to collaborate in a way. In this case, over a broker system. Future research. I think there are many operational aspects we can still think about. There are, we need to calibrate the models better. We do not have enough data by now for ride pooling services, or even for automated ride pooling services. So whoever has data, we would be happy to get them, or if you can share them. And I personally think that traffic state estimation and traffic state forecasts are going to be very, very important in the near future, because the traffic state determines a lot. There are a lot of routing algorithms, and there's a lot of routing in such pooling services. And if we do not know exactly what's the situation in the network, and if we do not have a clear forecast for the travel times, the service will have no good quality. And if a service has no good quality, it's not accepted by the customer at the end. So thanks for listening. One more time, the slide of our agent-based simulation framework, and I'm happy to take your questions.
Thank you very much, Klaus, for the great talk and also the great overview. So we have a couple of minutes for questions. There was a question posted on the doc. I think maybe Florian answered, or some of your colleagues, but maybe I will just repeat it for the sake of the audience. Somebody asked, is FleetPy or in general the tools you presented considering interactions between mobility providers, or are you planning on doing more research on that? I think this connects to the last part of the talk where you said, when you talked about this broker system. So
yeah, the broker system
that's pretty interesting.
Yeah, as the broker system itself is the idea how you could manage such a collaboration, and you could use FleetPy to simulate things like that. I hope I gave the same answer than Florian did in the document.
Yes, yes. There is consistency there, yes. Okay. Then I have another question, which is maybe a bit of, I haven't seen it in the presentation, but maybe you thought of that. Are you thinking about using this simulator also to kind of consider future scenarios in which you have to optimize the design of new infrastructure? Like now the setting is I have a network, I have a demand, I study some algorithms, but what if one of the varying variables is the network?
Yeah.
Can this be done?
I mean, I couldn't present all. We used it a little bit. Yeah, we tried also to optimize stops. So the question is, are you doing a door-to-door service, or are you using a bus stop-based system? Yeah, and the question is, it's much better to implement stops. That's, by the way, also what Moja did in Hamburg.
Yes, exactly.
Because you can save lots of mileage when you have implemented stops. So this is a first network question. But of course, we are thinking about network design also in comparison with other modes, especially biking, yeah, which plays a very, very important role in European cities at the moment, but we haven't done yet.
Okay.
But there are projects and ideas out there where we think about how could a city look like when it only would have an on-demand robo-shuttle service and biking.
Very nice. Thank you very much again, Klaus, for the talk on Saturday. It was very exciting, and thank you for being the icebreaker of this series.